Hello to everybody, my name is Camillo Dell'Ellis and I am professor at the Institute of Mathematics in the University of Zurich. My area of specialty is partial differential equations. And I'm going to present you today a problem which I baptized Kirsch and fondue problem, although it was not named this way by the mathematician who proposed it for the first time. Okay, so we could describe this problem in layman terms in the following way. You're actually eating fondue, and at a certain point you want to add some kirsch. Of course, you add the kirsch at a certain spot, and then you will have to stir the fondue in such a way that actually the kirsch gets properly mixed with the cheese. Well, in a sense, you can think about this problem as a good model for this. So let us put some mathematical terms into it. So first of all, we are going actually to have two-dimensional pots. So the problem is going to be two-dimensional, not three-dimensional. And I'm going to use the notation that BRX is the ball of center X and radius R in the two-dimensional plane. So this is going to be given by the points in R2, such that the modulus of Y minus X is less than R. You're going to think about it as the open ball. Okay? So initially you have your fondue, which is lying in the ball of radius 1, centered at the origin. And then you have your kirsch, which at the beginning is sitting in the ball of radius 1/2, centered at the origin. It's admittedly a big alcoholic fondue. Now we want to model the stirring, which will be modeled in the following way. So we think of having a vector field V, which is a map which is going from the unit circle into R2. This vector field is actually prescribing the velocity at which the various particles of the cheese and the kirsch move. So therefore this vector field is attaching to each point x a certain velocity vector v of x. So how do we model the motion of the cheese and the kirsch? We are actually imagining the following. So we denote by gamma x naught the path of each particle, and we just assume that the particle is starting at time 0 at the initial position x0, and it's then moving according to the vector field v that you have, which means in mathematical terms that the time derivative of this function gamma at every point t is actually given by the velocity field v evaluated at the point where your particle is standing. Okay? This is what is called an ordinary differential equation for the function gamma x naught. We now have a map phi, which is describing the motion of the whole system of particles. So we are just going to look at time 1 where the particle who started at time 0 at the point x is standing. So this is the definition of our map phi. Of course, you don't want to spill the fondue outside of the pot, which means that actually you want this map phi to go from the unit disk into itself. Well, then you have the following condition. V at the boundary of your pot has to be tangent to the boundary itself. You are also not allowed to compress cheese. So there is an important constraint that you are actually putting on the vector field V, and the constraint is that the divergence of V is divergence free. So this means the following: V consists of two components, V1 and V2, and then you know that the partial derivative in the x1 direction of V1 plus the partial derivative of the V2 direction in x2 is equal to 0. So each of V1 and V2 are two real functions of two variables. So this partial derivative over here means simply the following thing. We are taking the ordinary derivative of the function f thought as a function of one single variable when the other variable is frozen. Very good. So now you want to actually define what is a good mixture of fondue and kirsch. So initially your kirsch is occupying an area, a very specific area, which is 1/4 of the total. Later you want that actually essentially any portion of the pot contains a suitable amount of kirsch. Then you're actually going to require the following thing. So phi, we say, mixes at scale epsilon if for every point x0 in your pot, which is a distance epsilon from the boundary, the kirsch occupies an area in the disk of size epsilon centered at x0, which is at least 1/8 of the total area of this disk. You next want to measure the total amount of energy that you have put in the mixing. So the energy that you have applied is actually defined as the integral over the whole area of the sum of the moduli of the partial derivatives of your vector field. Alberto Bressan conjectured that anytime that you are mixing at size epsilon, you have to employ a certain amount of energy which is quantified in the following way. So there exists a constant C which is independent of anything we have said, so it's independent of epsilon and V, such that if your mat phi mixes at scale epsilon, then the total energy that you have employed is at least a constant times the modulus of the logarithm of epsilon. Maybe a few words about what we mean by this integral over the area given by the unit disk. If you're not familiar with this concept from higher dimensional calculus, you can practically compute this integral in the following way. So when you want to integrate your function f of two variables on the unit disk, what you're going to do is you're going to write the following iterative integral. So you integrate between minus 1 and 1, and then you integrate between minus square root of 1 minus z squared and square root of 1 minus z squared. And then you integrate the function f, first of all in the w variable, and then in the z variable.